In this lecture, I will try to derive the Fourier series for arbitrary interval and will solve some questions. As you know that so far we have the Fourier series for the interval when the length of the interval was 2 pi. Now in this lecture, I will derive a Fourier series when the length of the interval is arbitrary. That means it may be 2, 4 and so on. So Fourier series for change of interval. Let fx be defined in the interval c, c plus 2l. Now, so far we were taking pi in place of l. Now, this interval is general, so here l can be any number. Let us introduce variable z of where fz is periodic, or you can say that where size of z is 2 pi, and here you can see that our fx is defined in this interval, so we can say that the size of x is 2l. So due to proportion, we can write our z has size 2 pi and x has size 2l. So we can write z equal to pi x upon l. So assume that this is your z. Now if your x is c, that means if x equal to c, then your z will be pi c upon l. If your x is c, then our z will be pi c upon l, and it is a constant value, so let us assume it as d, c. And if x equal to c plus 2l, then our z will be, so if x equal to c plus 2l, then our z will be pi upon l, c plus 2l, and this can be written as 2 pi plus pi c upon l, and pi c upon l was d, so this will be your d plus 2 pi. So we can see that it means our z lies in the interval. Here you can see that our z lies in the interval d, d plus 2 pi. So our z lies in the interval d, d plus 2 pi, and our fx will be, now here your value of x will be Lz upon x, your x will be Lz upon pi, so this is your Lz upon pi, and because it is a function of z, say it is your gz. This is your function of z because Lz upon pi contains z, so we can assume this f of Lz upon pi some function of z. Now if fx converges due to the Dirichlet condition, then obviously gz will converge. Now if gz converges, then we will have the Fourier series for gz. So please note down these conditions. We will need this condition later on. Now here, thus we can say that gz is a function defined in the interval d, d plus 2 pi. Now, because gz is defined in the interval d, d plus 2 pi, and we have a Fourier series for this interval, which was gz equal to a naught by 2 the summation n equal to 1 to infinity a n cos nz plus n equal to 1 to infinity bn sin nz. This was the Fourier series. Now we can also write it as a0 by 2, then n equal to 1 to infinity an cos nz. Your z was pi x upon L. If you see the value of z, then it was your pi x upon L. So this will be your, as z was pi x upon L, so this will be your n pi x upon L, and further we will have n equal to infinity bn sin n pi x upon L. So this will be the Fourier series for gz, and gz and fx is same, so we can also say that this is the Fourier series for fx. So when the length of the interval, please remember that the length of the interval was 2l. Our fx was defined for the interval c, c plus 2l. So when the x was between, when your x lies in the interval c, c plus 2l, our Fourier series will be this one. Now what about the coefficients? Now where my a naught will be 1 upon my a naught will be, please remember this series of gz. From gz our a naught will be 1 upon, please remember that gz was defined for this interval, so our a naught will be 1 upon d to d plus 2 pi f z dz. This was your a naught for fz, sorry, for gz, because we have written the series for gz. Now because z is, as our z was pi x upon L, so from here our dz will be pi dx upon L. So, and the limit, if your z is d, when your z was d, then your x was c. So the lower limit will be c, and when your z was d plus 2 pi, here you can see that your z is 2 plus d plus 2 pi, and this was when x is c plus 2l. So for the upper limit we will get c plus 2l. So at z equal to d, our x will be c, and at z equal to d plus 2 pi, our x will be c plus 2l. And from here you can see that this will be your pi, not d, and you can see that here we have g of pi x upon L, and dz is pi dx upon L. So you can say that our a naught is pi, and pi is cancelled. So this will be 1 upon L, c to c plus 2l, and g of x was, your g of x was fx. So this will be your pi f pi x upon L dx. So, and this was your fx, sorry, g pi x upon L. Pi x upon L was your z, and this was your fx. You can see the layer notes. So when your length of the interval is c, c plus 2l, our a naught will be 1 upon L, c to c plus 2l, fx dx. Now let us compute an. With the similar region, our an will be 1 upon pi d to d plus 2 pi fx cos nz dz, because z was pi x upon L, so our dz will be pi dx upon L. So using the similar argument, we will have an equal to 1 upon L. Now for z equal to d, our x will be c, and then here we will have c plus 2l. This will be fx cos n pi x upon L dx. So this is your an. Similarly, our bn will be 1 upon L, c to c plus 2l, fx sin n pi x upon L dx. So this is the Fourier series for the interval c, c plus 2l, where the Fourier coefficients an is this one, and you can also assume here n equal to 0, and if n is 0 we will get a naught, and here we have bn. Now I will summarize this result. Thus we can say that if your x lies in this interval c, c plus 2l, our Fourier series is fx equal to a naught by 2 plus n equal to 1 to infinity an cos n pi x upon l plus n equal to 1 to infinity bn sin n pi x upon l. So this is your Fourier series, and where my an will be 1 upon l c to c plus 2l fx cos n pi x upon l dx, and we can start n from 0. If n is 0 we will get a naught, and bn will be 1 upon l c to c plus 2l fx sin n pi x upon l dx, where n will be from 1 to 3 and we will start from 1. So this is the Fourier series for the interval c, c plus 2l. Some author used another formula. Now if suppose that if your length of interval, suppose that your length of the interval is b minus a. So if here you can see that your length of interval is 2l. So if 2l equal to b minus a means the length of the interval is the length of interval. So if this is the length of interval, then you can see that your L will be b minus a by 2. So then your series will change accordingly. So therefore your fx will be a0 by 2, n equal to 1 to infinity an cos. You can see that your L will be, from here we will get L equal to b minus a by 2. So here we will get 2 cos 2 n pi x upon b minus a, and here we will get bn sin 2 n pi x upon b minus a, and the Fourier coefficient will be 1 upon L, where L is b minus a by 2. So this will be your an equal to 2 upon b minus a, and the interval is from a to b. So the length of the interval will be, and the interval will be from a to b fx cos 2 n pi x upon b minus a dx. Similarly here we will have 2 upon b minus a, then the interval from a to b fx sin 2 n pi x upon b minus a dx. So this will be the Fourier series when the length of the interval is b minus a. Now let us find out some particular series. Suppose that c is minus l. So if c equal to minus l, then the length of the interval will be from minus l to plus l. So note, say this is your first series. If your c equal to minus l, then length of interval will be, then your interval is, then our x will lie in this interval minus l comma l. So this will be your interval. Now if this is interval, then our Fourier series will be this one, and where my Fourier coefficients are, c is minus l, so this will be your minus l to plus l, and bn will be from minus l to plus l. So this will be your Fourier series in the case when x lies between minus l to l. So this will be the Fourier series for the interval minus l comma l. Okay, I think there is no problem in this one. So for the interval minus l comma l, this is the Fourier series, and these are the Fourier coefficients. Now suppose that c is 0, second series. If c is 0, then our length of the interval will be 0 comma 2l, and if c is 0, then this will be your Fourier series, and as our limits was from c to c plus 2l, now as c is 0, so this will be your 0 to 2l, and here we will have 0 to 2l. Now this is the Fourier series for the interval 0 comma 2l. This is your Fourier series, and these are the Fourier coefficients, which are also known as Euler coefficients, Euler formulae. So this is your Fourier series for the interval 0 comma 2l. If interval is 0 comma 2l, we will have the limit 0 to 2l, and again here we will have limit 0 to 2l, and L will be the length. Remember that here we have the interval 0, 12. I am not talking about the half Fourier series. So 12 means the upper limit. Now in the third case, I am discussing the half range series. So for the third case, if fx is even, then now if your fx is even and in the interval minus L comma L, then our Fourier series will be, now if the function is even, then you can say that if the function is even, then our a naught will be, okay, I am writing it again. So if your fx is even, then our a naught will be 1 upon L minus L to L fx dx. Now as the function is even, so this will be your 2 upon L 0 to L fx dx. Okay. Now suppose that, okay, this is your a naught, and a will be 1 upon L minus L to L fx cos n pi x upon L. Now fx is even, cos is even, so this will be your 2 upon L 0 to L fx cos n pi x upon L dx. And bn will be 1 upon L minus L to L fx sin n pi x upon L. Now as function is even and sign is odd, so this will be your 0. Therefore our Fourier series in this case is Fourier series is fx equal to a0 by 2 plus n equal to 1 to infinity an cos n pi x upon L. So this is your Fourier series when your function is even. Now the fourth case, let us suppose that the function is odd. Now if the function is odd, then our a naught will be, now because the function is odd, so this will be your 0. So you can say that this is your 0. Again an, here the function is odd, cos is even, so their product will be odd, so this will be your 0. And bn is 1 upon L minus L to L fx sin n pi x upon L dx. Now fx is odd, sin is odd, so this will be 2 upon L 0 to L fx sin n pi x upon L dx. Therefore Fourier series is fx equal to summation n equal to 1 to infinity dn sin n pi x upon L. So this is your Fourier series. Evaluate or find Fourier series for fx equal to x when your x lies between minus 1 to 0, and this is your x plus 2 when your x lies between 0 to 1, and reduce the value of 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. Solution. You can see that your interval is from minus L to plus L. That means here our interval is minus 1 to 1. That means your L is 1 and the length of the interval is 2L. So our Fourier series is fx equal to a naught by 2, n equal to 1 to infinity, an cos n pi x upon L, L is 1, so this will be your an cos n pi x, plus n equal to 1 to infinity, bn sin n pi x. So this is your Fourier series where my a naught will be 1 upon L minus L to L fx dx. And this will be, as L is 1, so this will be your minus 1 to 1 fx dx. Now let us evaluate this one. Okay, here is the base 2. So this is equal to, we can partition this interval in two parts, one from -1 to 0, for which the value of the function is x, and for the other part, when your x is from 0 to 1, the value of the function is x plus 2. So integration of x will be x square by 2, then limits from -1 to 0, and here the integration of x plus 2 will be x square plus 2x, and then limits from 0 to 1. Now here upper limit will be 0 and lower limit will be half. So this minus half, and here the upper limit will be half plus 2. So this is your 2. So our a naught is 2. Now an will be 1 by L. So L is 1. So this will be your from -1 to 1 fx cos n pi x upon L, and L is 1. Now let us break it in two parts. From -1 to 0, our fx was x, and then from 0 to 1, our fx is x plus 2. Now we can integrate this using the Bernoulli's rule. So we can write it as the term x into integration of cos, which will be your sin n pi x upon n pi. Then we will have minus sign, and the differentiation of x is 1, and the integration of sin will be minus cos n pi x upon n pi, and the limit from 0 to -1 to 0. Then we will have plus sign 0 to 1, and the integration of this bracket will be x plus 2. Integration of cos will be your sin n pi x upon n pi, then minus sign. Differentiation of x plus 2 will be 1. Integration of sin n pi x will be minus cos n pi x divided by n square pi square, and the limit will be from 0 to 1. Now, as we know that our sin 0 is 0, so upper limit will be 0. Again, sin n pi is 0, so the first term will be 0. For here, for this term, our upper limit will be 0 as sin x is 1, and so we will have sin n pi, and that is 0. And again, its lower limit will be 0 because we have sin 0. So let us start with this term. This will be your minus minus plus. Now for the upper limit we will have cos 0, so this will be your 1, and for the lower limit we will have cos minus n pi, and cos minus n pi is same as cos n pi, so that will be your minus 1 to power n. So this is your second term. Third term is 0, and again for the fourth term, here we will have n square pi square. So this is your n square pi square, and here again this is minus minus plus, so we will have n square pi square. Cos n pi will be minus 1 to power n, and cos 0 is 1. So we can see that these two terms will cancel each other, so our an is 0. This and this term will cancel each other, so our an is 0. Now let us compute bn. So bn will be your 1 upon L, L is 1, minus 1 to 1 fx sin n pi x dx. And let us break our integral from -1 to 0, where the function of fx is x, and for the second part, the value of fx is x plus 2. Now let us integrate these two terms. So for the first part, we will have x, integration of sin will be minus cos, and then we will have minus sin, and integration of cos will be sin n pi x divided by n square pi square, and the limits from -1 to 0. Then similarly we will have x plus 2 minus cos n pi x upon n pi, then we will have minus sin n pi x upon n square pi square, then the limits from 0 to 1. This term will be 0 for x equal to 0 and x equal to -1. Again, this will be 0 for x equal to 1, x equal to 0. Now the upper limit of this term will be 0, and for the lower limit our x will be minus 1. So this minus and this minus will be plus, and as we have a minus sign, so this will be a minus 1. So cos n pi is minus 1. So this will be your minus 1 to power n upon n pi. And here our x is 1, so this will be your 3. So that means minus 3 cos n pi, which is your minus 1 to power n upon n pi. Now for the lower limit we will have x equal to 0. So this will be your 2 into cos n pi, that means minus 1 to power n upon n pi. So again this will be your minus 3 minus 1, that means minus 4. So this is your minus 2 minus 1 to power n upon n pi. So this will be your Bn. Again I think there is some mistake. Let us find out this mistake. For this upper limit our x is 0, and for the lower limit we will have x equal to 1. So this will be your cos n pi. So cos n pi is minus 1 to power n upon n pi. And here the upper limit will be, so here is the mistake. Now for the lower limit our x is 0, so this will be your cos 0, and cos 0 is 1. So this is equal to minus, so this will be equal to 2 upon n pi 1 minus 2 times minus 1 to power n. So this will be our Bn. Okay, now this is correct. So this is Bn. So our Fourier series is fx equal to a0 by 2 plus n equal to 1 to infinity an cos n pi x upon l was 1 plus n equal to 1 to infinity bn sin n pi x. Now as our a0 is 2, so this will be your 1, and an was 0, so this term is 0, and bn is 2 upon n pi 1 minus 2 minus 1 to power n sin n pi x. So your fx is equal to this one. So this is our Fourier series. So this is the answer. Now we have to deduce the sum of that particular series. For that, here our x was, when your x was from minus 1 to 1. In that case our Fourier series is this one. Now as we have to deduce the sum of that series, so let us put, we cannot put x equal to minus 1, otherwise this will be your sin 0, because sin n pi is 0. And again we cannot put x equal to 1, otherwise again, this term will become sin n pi, and that is 0. So let us put any number between minus 1 to 1. So I am putting x equal to half. So if x is equal to half, and remember your fx was x when your x lies between minus 1 to 0, and this was x plus 2 when your x was from 0 to 1. Now if x equal to half, then half will lie in this interval. So the value of the function will be x plus 2, that means half plus 2. So the value of the function is half plus 2, and in the right hand side we will have 1, n equal to 1 to infinity 2 upon n pi 1 minus 2 times minus 1 to power n sin n pi by 2. When x equal to half, our Fourier series will be this one. So now let us evaluate this one. So this is your 2 to the 4 plus 1, that means pi by 2 equal to 1. Then we can take 2 upon pi common. Now if n is 1, then this will be your sin pi by 2. Sin pi by 2 is 1. So if n is 1, then this will be your, if n is 1, then this will be your minus 1. So this is your 3. So we will have 6 upon pi. So if n is 1, then we will have 1 by 1. Now if n is 2, then this will be your sin pi, and sin pi is 0. And if n is 3, then again we will have minus plus 2, and this will be your 3, and we have already taken 6 common. So if n is 3, we will get sin 3 pi by 2, and sin 3 pi by 2 is minus 1. So we will get minus 1 by 3. Similarly, we will get 1 by 5 and so on. So in the left hand side we have 5 by 2 minus 1 equal to 6.5, 6.5, and in the bracket we will have 1 minus 1 1 by 1 minus 1 by 3 plus 1 by 5 and so on. So this is your 5 minus 2 means 3 by 2 equal to 6.5. 1 by 1 minus 1 by 3 plus 1 by 5 and so on. So this is equal to pi by 4. So the sum of this series is pi by 4. Let us solve one more question. Find the Fourier series of fx equal to pi minus x point 2 in the interval 0, 2. Solution. Please note down that here we have to find out the Fourier series, not the half range series. So our length of the interval will be 0, 2l, as we have to find out the Fourier series. If the question is to find the half range series, then our length of the interval will be 0, l, and in that case we will take l equal to 2. But as we have to find out the Fourier series, so our length of the interval will be 0, 2l, where l is 1. So therefore here length of interval is 0, 2l. So our l will be 1. Therefore Fourier series is fx equal to a0 by 2, n equal to 1 to infinity, an cos n pi x 1l plus l is 1, so this is your cos n pi x, plus n equal to 1 to infinity, bn sin n pi x. Now let us compute the Fourier coefficients, Euler formulae. Therefore your a0 will be 1 upon l. Now l is 1, so this is your 1, 0 to 2 fx dx. Our formula will be 1 upon l, 0 to 2l fx dx, as the length of the interval is 0 to 2l. And this will be a 0 to 2 pi minus x point 2 dx. And this will be equal to pi x minus x square by 2 from 0 to 2. So this will be a 2 pi minus 4 divided by 2, that is 2. So this is your pi minus 1. Now our an will be 0 to 2 fx cos n pi x dx, and this will be equal to 0 to 2 1.2 pi minus x cos n pi x dx, and so it is equal to 1 by 2. Now its integration will be pi minus x, integration of cos n pi x will be sin n pi x divided by n pi, then we will have minus sign, and its differentiation is minus 1, so this will be a plus, and integration of sin is minus cos, and we will have limit from 0 to 2. Now here you can see that if your x is 2, then we will have sin 2n pi, which is your 0, and if x is 0, then we will have sin 0, which is again 0. So from here our upper limit will be, this is your 2 into n pi, we can take minus sign common, so this will be minus 1.2 n pi. Now upper limit will be your cos 2 n pi, and lower limit will be your cos 0. As cos 2 n pi is 1 and cos 0 is 1, so this is your 0. So again our an is 0. Now let us compute bn. bn equal to 1 upon l, 0 to 2l fx sin n pi x upon l. Our l is 1, so this will be your 0 to 2 fx is pi minus x point 2 sin n pi x dx. So on integration, this will be your minus pi minus x, integration of sin will be minus cos, then we will have minus sign, and differentiation of this will be your minus, so this will be plus, and integration of cos will be minus sign. Here we will have n square pi square. So this is from 0 to 2. Here the integration of sin will be minus cos, and in the denominator we will have n square pi square. Now let us evaluate this one. You can see that our this term will be 0 because Sin 2 n pi is 0 and sin 0 is 0. Now let's compute this one. Now if x is 2, then this will be your, we can take minus sign common, so this will be your minus half. Now if x is 2, then the upper limit will be pi minus 2, and this will be your cos 2 n pi, and cos 2 n pi is, we can also take this 2 n pi common, so we will have this one. Now in the bracket, if x is 2, then we will have this term and cos 2 n pi, and cos 2 n pi is 1, so this is your 1. Now if x is 0, then this will be your pi, cos 0 is 1, so this will be your minus pi. So we will have minus 1 upon 2 n pi. In the bracket, we have pi minus 2 minus pi, so this will be minus 2, and our bn is 1 upon n pi. Therefore, Fourier series is, Fourier series is fx equal to a0 by 2, n equal to 1 to infinity, an cos n pi x upon l, l is 1, n equal to 1 to infinity, bn sin n pi x upon l, n is 1, l is 1. Now our fx was pi minus x upon 2, our a0 was pi minus 1, so this is your pi minus 1 by 2, an was 0 and bn is 1 by n pi, so this will be your 1 upon n, then in the bracket we will have sin n pi x upon n. So this is your answer.